In the previous class, we have derived the covariant form of Dirac equation. And the original Dirac equation is like that. And after we define gamma matrices, it was possible to express this one in covariant form. Okay. Let us go back to the original equation. We have derived the Lagrangian like that. Not derived. We just checked this Lagrangian gives the equation of motion for psi bar, right? But for the educational purpose, let us check inverse transformation. From the Dirac equation, we take the complex conjugate and multiply gamma 0. Let's see what happens. If I take the Hermitian conjugate, derivative of psi becomes the derivative of psi dagger, and I becomes minus I, and gamma matrix is appears on the right side, and I have multiplied gamma 0 to the right side, so its order does not change. However, psi bar is psi dagger gamma 0, right? And let me multiply beta squared, that is 1, and actually that is gamma 0 squared. Insert gamma 0. Then gamma 0 combines this one. You know, gamma 0 is constant, so it does not matter whether it is taken derivative or not, right? So this guy is same as this one. After taking the derivative, we can multiply gamma 0, but before taking the derivative, you can multiply gamma 0 to make psi bar. And gamma 0, gamma mu dagger gamma 0, we have homework that to prove this one is exactly the same as gamma mu. Okay. And this one, if I transform this psi with dagger and gamma 0, it is by definition psi bar. So if I combine these two with negative sign on it, I have minus I round mu psi dagger gamma mu minus m psi dagger psi bar. So this equation can be obtained by taking the Hermitian conjugate and multiplying gamma 0 to the right side from original Dirac equation. So equation of motion for psi bar can be derived from the equation of motion for psi. If you do the same calculation for the variation of psi bar, you should obtain this. This is the equation that was obtained by varying psi. So another homework is, if you make use of this Lagrangian, you should be able to find, by minimizing the action, you should be able to find the Dirac equation directly without making transformation. So what about considering the combination of these two contributions? So if I combine these two and take the average, then the form becomes like that. After defining this kind of strange notation, if I take the derivative with left-right arrow, that means take the derivative to the right side with positive sense and take derivative to the left side with negative sense. Then I can absorb this negative sign, and sum of these two contributions is just I times psi bar gamma mu round mu that is acting to the right and left. If you act to the right, it is positive sense, and to the left, it's negative sense. So if I want to keep the mass term with the same normalization, because they are both the same. So I just use minus m psi by psi, but I have 1/2 I psi bar gamma mu left right covariant derivative psi. So homework is derive psi in this complete Lagrangian to find the equation of motion for psi bar. And psi, derive psi bar, you know, psi bar is just the psi dagger times gamma 0. I just multiply the constant matrix. So gamma 0 is not buried. So you do not have to bury psi dagger. You can directly bury psi bar. So that is another homework. Variation of psi bar and the variation of psi dagger both give the same result. And that is the Dirac equation. Okay? So now we have found that the Lagrangian for the free particle, that is actually for the spin 1/2 massive free particle, is like that. Another homework is number 3 from equation of motion by integration derive Lagrangian. Okay? Formed from. That is the way we usually did, right? So let us write down the Lagrangian. So anyway, in general, you can write these two terms, but for convenience, let me, usually, in usual textbook, we usually write just a single contribution. But if you want, you can always flip the sign and take the derivative to the psi bar, and you can obtain the complete notation. So this is Lagrangian for the spin 1/2 particle, and this is free spin 1 particle. This is the Lagrangian for the free photon. What happens if the spin 1/2 particle interacts with photon? There must be some contribution proportional to current and the gauge term. But as we already did several times, that can be obtained by replacing the covariant derivative with the gauge covariant derivative. You know, this is a round mu. This round mu is replaced with the gauge covariant derivative, round mu plus IQA mu. Then just consider a mu dependent term. The difference between this and the case for the charged scalar particle is that charged scalar particle that had in the Lagrangian, they have double derivative. So we had a mu dependent term, two kinds of a mu dependent term, linear term and a mu squared term. But in this case, only a mu dependent single term appears. And if I want to find this kind of one, I just substitute this IQA mu only, because this one gives the free particle Lagrangian. So if I substitute IQA mu to this part, I have psi bar I gamma mu and IQA mu, right? And psi. I meets, so I have negative sign and charge Q and psi bar gamma mu psi A mu. Okay? So minus J dot A means that J mu current is Q psi bar gamma mu psi. So this is the current, interaction current. Then what is the Feynman rule? Feynman rule is just minus I. If a photon meets, if an electron meets a photon in real interaction, electron E minus, muon is another the different family of electron, but electron muon that they can collide together and virtual photon exchange, then this vertex is actually minus IQ gamma mu, because this is a wave function for the initial electron and final electron. Oh. And if you solve the Dirac equation, you will find the psi are composed of positive energy solution and negative energy solution. And positive energy solution is for the electron, and negative energy solution is actually the same as the charge conjugation state. That can be studied later, but in that case, electron spinor is U for the initial state, U bar, that is U dagger gamma 0, that is for the final state, and V is the final state for the positron, because negative energy solution goes backward from the future to the past, and V bar, which that is a V dagger gamma 0, that is an initial state positron wave function, something like that. So that wave function will be pulled out if we compute the Feynman rule, then operate the matrix element only. So minus I current, so minus I Q gamma mu is the Feynman rule for the electron and photon. Another important thing we find is this is a Lorentz scalar, so J mu must be 4 vector, right? And what about this? This is gamma mu, and this gamma mu sandwiched by psi bar and psi transforms like a 4 vector. Even though right now we have not derived the Lorentz transformation properties for the psi and this object, but without doing anything, just the requirement shows that this one must transform like 4 vector. And we can also construct this kind of object, and later we will learn that this is just a scalar. Okay, let us go back to the original definition for the psi bar. That is a psi dagger times gamma 0. And decompose gamma mu in terms of original Hermitian matrices beta and alpha, then it is beta, beta, alpha. If beta meets beta, beta squared is 1, and beta, beta, alpha, that is all alpha. Haha. Because we know that this must be a current zeroth component is probability density. Haha. Psi bar psi. Psi dagger psi is the probability density of the wave function. That's correct interpretation. And I don't know yet, but it must be the velocity of the particle times probability density. That is my guess, and you will find that it is true. That's it.